Ladies and gentlemen, John Fragalla.
Thank you for having me today. So today, I want to go through a couple things on the topic today. So first, I want to discuss the benchmark setup that I put together to compare the clients of actually 4 clients that I actually compared. Talk about the IOR parameters that I used and the settings, Lustre client methodology and tuning that we went through, and then I'm going to go through 2 different comparisons of the client performance. One is solely just comparing single thread performance, and then the other comparison is really looking at the throughput comparison of maximizing storage performance. And then formalize it and share all the data results, and then come up with some summary remarks that I found quite interesting looking at the comparisons. So the storage architecture was based on a Xyratex Cluster Storage 6000 scalable storage unit with grid RAID OSTs. So the rated storage performance for this architecture is approximately 6 gigabytes per second read or write using IOR. So that was the goal for the throughput test, is to get 60 gigabytes per second read or write across all client versions that I used. The client hardware, it was very modest, 8 clients. Each client was configured with QDR InfiniBand, 48 gigs of memory, 12 cores, and I used Scientific Linux 6.5 on the clients with stock OFAD. So let's talk about the IOR parameters I used. So I used MPI run to execute IOR across all 8 clients, and I used the by-slot distribution. So at a minimum, I started with 4 slots per client, or 4 tasks per client, and scaled up the number of slots per client by distribution of 4, and then by that, when we ran out 4 tasks, then I added 4 additional tasks per client. The parameters that I used were file per process. I standardized on direct I/O instead of buffered I/O. And I used a transfer size of 64 megabyte because the grid OSTs are trying to maximize performance. And then I used really large block size per task because I wanted to use the Stonewall option to read and write. So I was writing for 4 minutes, then read for 2 minutes. The Lustre settings that I would use for the output of the data was a stripe count of 1 and a stripe size of 1 megabyte. So the 4 client versions I compared was 189, 216, 243, and 251. And the methodology was that we enabled and disabled checksums, and in each time that we enabled and disabled checksums, we ran through the same iterations of the client tuning parameters of the max RPCs in flight and the max dirty MBs. And you can see that I kept with the 1:4 ratio of max RPCs in flight and max dirty MBs. So we started with 32 max RPs in flight and 128, so on and so forth. In each of these iterations, we had checksums disabled and checksums enabled. As I go through the presentation, you're going to see graphs of all data results of checksums disabled, and you see tabular results of the impact of when checksums were enabled. So let's focus on the single thread performance first. So this is using 1 task on a client comparing reads and writes. So this table is with checksums disabled with only looking at a write performance. So you can see here, the top line in black is our 1.89 write single thread performance. The red line at the bottom was the 2.16, and the kind of the overlapping line in green and blue were 243 and 251. So what this key takeaway is that 189 single thread performance still is far better than the client versions that I benchmark. But the positive takeaway is 243 and 251 vastly was improved in performance compared to the 216 client code. You take the same results and you look at read performance with checksums disabled. And again, 189 is at the very top, and the very bottom is 2.1.6. And very similarly, 243, 251 follow the exact same performance curves. So regardless of the RPCs in flight, because there's only a single thread, these are pretty much the performance of a single thread performance when looking at these client versions. And again, the positive takeaway is 243 and 251 vastly improved against its former predecessor of 2.1.6. Now, what I also did was I wanted to isolate single thread performance, so I looked at let's now enable checksums on just single thread performance numbers. So when we enable checksums, you'll see that the performance impact on all 4 client versions were the biggest on 189. So on reads, it was up to 19%. On writes, it was up to 35%. Interesting data, though, as we went to the 2.x client code, the checksum's impact on those single-thread performance was much less, which was very encouraging to see. You'll see as 2.4.3 and 2.5.1 almost had the same performance impact of 6% less performance impact on reads and about a 1% performance impact on writes, which was very encouraging to see that. Historically, I've always thought checksum's impact was much larger than that, but with the 2x client code, it's much smaller than that. So looking at that, so the next couple of slides now is not looking at now single-thread performance, now looking at how to maximize storage throughput. And the key goal was, how do we get 6 gigabytes per second read and write using all 4 client versions? So we're going to start with 189 and have it compared to itself, and then talk to all the 4 client versions, and then overlap the relevant client versions to maximize performance. So let's start with 189. So 189, we started with the max RPCs in flight with 32 and 128, and incremented by a 4x version on top of that. So we started with 1 node with 4 tasks, increased that up to 8 nodes, 4 tasks per node, or 32 threads total, and then added up more threads. So you added up to 8 nodes, 64 threads, and then 8 nodes, 96 threads, because we have 12 cores, and I wanted to isolate a thread per core. You can see with 189, with the more threads that we added, the performance all across max RPCs in flight and max 30MP had no impact difference between all different thread counts. So relatively, we were able to hit the storage throughput that was required at a minimum of 60 gigabytes per second using 189 client code. And the different settings in max RPCs and max 30MBs had really no impact on the performance for reads and writes. Now 2.1.6, regardless of what I tried to do to get the performance impact up on 2.16, the highest read performance I could get was just roughly over 5 gigabytes per second. And the highest write performance was right around 4 gigabytes per second, maybe just a tad north of that. But you can see that with the more threads, you can see the performance increasing. But then you could also see that, in general, the different client settings really didn't have an impact on trying to maximize the storage throughput. So with the 8 clients, we saw at most 4 gigabytes per second writes, nowhere near what the storage architecture was able to push. So now let's go to 2.4.3. So 2.4.3 is where this was actually very interesting. The different client settings and the different threads actually had an impact in storage throughput. So you can start seeing with the color scheme here that with the larger max RPCs in flight, around 128 or 256, we're able to maximize reads and write performance almost equivalently to 189 client code. So with the smaller RPCs in flight, like 32 or 64, we could not get over to the maximum throughput of that storage architecture, 60 gigabytes per second. As soon as we got over 128 max RPCs in flight, we were able to get that write performance up. We were able to get the read performance up. But once we got to 256, both reads and writes for 2.4.3 maximized storage throughput. But interesting data on this curve for the writes is that the sweet spot was about 8 clients and 32 threads. What I found interesting was with the green curve at the 128 max RPCs in flight, actually did a diminishing returns of performance when we actually went to 64 threads, and then even worse around 96 threads. The 256 RPCs in flight held quite well between 32 threads and 64 threads, but then tapered off when we got to 96 threads. The reads, however, kind of standardized about the same, right around 60 gigabytes per second, hovered around that with the 256 and 128 max RPCs in flight. Now take note of this curve, and let's look at 2.5.1. 2.5.1 almost followed the same curve on reads. The little bit difference on performance was the slight improvement on the max RPCs in flight for 256. So this is 2.4.3, and we're looking at the blue curve on the top left chart. And then you can see that there's almost parallel performance, or no performance degradation when going from 32 threads to 64 threads. So slight performance improvement On the right's looking at the 256 max RPCs in flight. Now, looking at the overall storage throughput, meaning that we standardized from 4 threads to 96 threads, and we took an average of the data to look at the performance impact when checksums were enabled. And you can see very different results when looking at throughput results versus single thread performance results. On the 189, you see that the checksum impact is negligible to about 2% for reads or writes. With the 2.16, it was a little higher, around 22% with the 32 max RPCs in flight, but it actually got favorable in some results, on the right specifically, no more than 10%. Very encouraging on the 243 and 251 when checksums were disabled. The impact was within 5% on average, possibly 6%. So not as large of an impact to doing checksums enabled for 243 and 251 clients. Now what I wanted to do, knowing that 2.1.6 I could not get the performance up, I then took 189, 243, and 251 and overlapped the results together for reads and writes so we could actually look at a really direct comparison. So this chart just looks at the 3 client versions, and then you see some dotted results. Those are the results I don't want you to focus on. Those are the ones that are 32 max RPCs in flight and 64 max RPCs in flight that we couldn't get the storage rated performance of 6 gigabytes per second, reads or writes, for those 2 clients. But what you can see here, the client of 189 scaled quite well, and in standardized, it didn't degrade as much as we went to the top north of 6 gigabytes per second on writes. When we increased the max RPCs in flight to 128, or 256, and again between 32 and 64 threads, 243 and 251 was almost performing equivalently to 189 clients. But then when we got to more threads, it tapered off a bit. Same thing with the read performance. I didn't want you to focus on the max RPCs in flight of 32 or 64. That's why they're a little lighter and dotted. I wanted you to focus on the max RPCs in flight of 128 and 256 for the 2.43 and 2.51 clients. You can see as well that they actually were able to sustain the storage rated performance for reads. So the overall takeaway is that with the right client tuning parameters of 243 and 251, we can sustain the rated storage performance of 6 gigabytes per second. With 189, regardless of the client tuning parameters, the biggest impact on performance with 189 was the number of threads we used. So the direct comparison to maximize performance results was on 189, we looked at the far left table, which is I think gray in that scale, or black. Those are the max RPCs in flight of 32, max 30 MBs, and 128. Those resulted, they gave us the maximum performance for the storage enclosure. On 2.16, these were the results that maximized the client performance when we looked at 2.16, and again, that was the lowest performing benchmark result that I had. And you looked at the blue and green, which is 243 and 251, with 256 max RPCs in flight, performance within range of the 189 clients, which is very encouraging where we were from the 2.16 client code. So interesting results from analyzing the raw data that we collected. In general, 189 clients perform the same regardless of client settings. Encouraging news is 243 and 251. Well, not encouraging news. Surprising, actually, was I actually thought the 2.51, before I ran these benchmarks, would have performed slightly better than 243. But you can see that, in general, the curves follow the same performance metrics when looking at client setting and number of threads increased. And then at a minimum for this benchmark setup, we needed to increase the max RPCs in flight to 256 to even get to the maximum storage throughput. And then the rule of thumb where we traditionally use max RPCs in flight is 1/4 the size of max 30 MBs, or in inverse is max 30 MBs is 4x max RPCs in flight. With the later client versions, in my opinion, those rule of thumbs is not holding true anymore. We could actually see a max RPCs in flight at 256, and maybe your max 30 MBs equaled the same value of max RPCs in flight. So those were interesting results as well. In summary, looking at all the raw data, 189 still provided the same highest performing single thread performance results. But encouraging, 243, 251 vastly improved over its predecessor 2.1.6 for single thread performance. With the right client settings, 243, 251 can maximize the storage throughput. 2.16, regardless of any tuning parameters we could do, just underperformed. And the checksums impact on the throughput test were not big, within 6% of the checksums when they were disabled results. And again, 243, 251 almost performed similarly in these benchmarks that I tabulated for the performance curves for maximizing storage throughput. Thank you. Any time for questions?
Hey, John, what was the setting that you used for your benchmarks?
Can you repeat that, Nirmal?
No, what was the setting that you used? Did you use a Cray, or was it just a flat tree?
It was a standard x86 clients on a flat InfiniBand network, directly mounting a cluster storage 6000 scalable storage unit.
Okay. QDR, FDR?
That was QDR on the clients, FDR on the storage, and FDR on the core switch.
Okay. So on the testing we did, we didn't need to go up to 256 on the max RPCs in flight because we are oversubscribed on the Cray side.
And again, I only had 8 clients, so that's also plays a factor on the RPCs in flight. If I had more clients, the results could have been slightly different. The max RPCs in flight setting could be much less if I had more clients.
Yeah, that's what I wanted to point out. So we didn't have to, we got better performance with 2.4 compared to 186 with just a max RPC in flights of 32.
Good, thanks.
Hi there. So this is a test of Lustre client performance. On your server end, was that always locked down as Lustre 2.51?
No, that was locked down. I will revisit that. I actually probably misstating that. That was using a Xyratex Lustre 2.1 variant server-side code. That was static across the benchmarks. So this is 189, 243, 251, and 2.16 clients running against the Xyratex variant 2.1 server version of Lustre. I did not do any benchmarks on the server side other than the 2.1.
Okay, because I'm wondering if the server side does affect, right, the client side as well, if it's locked down.
That is true,
right.
and we'll definitely revisit that when we move to that newer client, to that new server side. Definitely look at the benchmarks and do the same performance comparisons. Yep. I think we have a question back there or up front. Yep. Yeah.
Thank you. I was wondering whether you made some tests regarding this max RPC in flight, varying the average size of file. So, because this measure are made with a given average size of the file, or what? I mean, whether did you test something with the small file, like a few kilobytes?
No, I did not. So I standardized. I wanted to keep almost everything static versus just the client settings and the client code. So the IOR benchmark was static across all benchmark settings. So I used a transfer size of 64 megabyte, and I used a block size big enough so I could write for 4 minutes and then read back that same result for 2 minutes and using direct I/O.
Thank you.
Because the goal for me was just to maximize client performance and not look at performance variation of small file versus large file, random versus sequential. I wanted to keep almost everything static and just look at the client settings as the variable that changes.
John?
Yes.
I think you just answered my question as well, which is, why didn't you look at shared file performance?
Timing. and that was on my things to do, but I knew I only had 30 minutes, so I had to pick where I wanted to present the data. So single shared file is actually something that would be interesting to look at as well.
And do you have any preliminary numbers that you could even talk about?
I have preliminary numbers on a customer benchmark we did with 189 client code, but nowhere where we do the comparisons between the two. But that's something that would be on the task I would like to do and complete in probably put a paper together, present another conference on.
Okay. And maybe Brett, maybe.
Yeah, I find, a single shared file benchmarking is an art, so yeah. And it also depends on, the number of clients, the number of OSTs, all those things play a factor how you set up IOR for single shared file.
Brett Kettering's talk tomorrow from Landl, I think, will have a little bit more about shared file.
Good.
Great.
So I've got a question.
Yes.
So in our environment, you've got a poor sap that decides he's going to go to graduate school in chem informatics. And so he shows up, and the director of the program says to him, we've got this cluster. And, if you'd like to graduate, perhaps you should administer this cluster. So let's imagine now that it's got a Lustre file system attached to it. And this poor sap doesn't really even know where to begin. What can you, Intel, anybody do to make it so this guy doesn't have to read your paper, tweak everything, figure out that his max dirty megs has to be, RPCs in flight over 4. So what can be done? What do you think?
So I know that in part of OpenSFS, there's that working group for benchmarks, right? So what I try to do, and I haven't released this paper yet that I've written. I created a paper internally for our field team, so they could say when we rate a storage performance, these are the tuning parameters and IOR setups. So we do baseline testing, make it very easy. And that's very specific to the cluster store architecture. Now, when you go to another architecture, it can be very different because they have harder RAID caching or not. The number of size of the OSTs is different. The disk drive technology is different. So it's hard to say it's a standard, but I think what we could do in the working group, which I've been meaning to join the benchmark working group, is to look at a standard IOR test that just does baseline, and then a vendor could come in and say, specifically for us, these are the tweaks that we recommend. Or these are the characteristics of an architecture, and these are the tweaks you look for to try to make it simple or simpler for somebody new that coming into Lustre. So I agree it's a challenge, and we see things different every day, that even a commercial code is going to perform differently than the synthetic benchmark. So the more exposure, the more data that we release, I think it's going to be beneficial for the community as a whole.
Okay, thanks, John. I mean, I look at the sign above your head, broadening the Lustre community, and I'm saying, well, you just laid out a whole set of different parameters that need to be tweaked. When you buy an expensive sports car, do you really need to tweak all the pieces, parts in order to get it to go? All right, thank you.
No problem. Nope.
Hi.
Hi.
Do you have any information about the variance that you got while running this test? And along that line, how many times did you run each?
The iterations? Mm-hmm. Yeah, so I did one iteration for test. So I just created a script, and I let it run overnight. And so basically, we just let it run. And what I did was, between each write and reads, every benchmark had different output files. So I didn't reuse the same output files. I had different names to make sure we were not trying to rewrite or reread or reuse the same file names. But I didn't do anything creative there. I didn't clear Linux page caches on the clients. I didn't do anything between reads and writes. I wrote the data 4 minutes. I slept for 5 seconds. I read the data for 2 minutes, read the data, on to the next test. And then when we went from different client versions, unloaded Lustre modules, created and compiled a new client, mounted the file system, and reran the same scripts over and over again. So nothing unique, nothing creative, just very standard.
Hi, John. This is great work. Thanks. And my question is that, did you, by any chance, look at 2.42?
No, I actually was going to look at it, but there was no reason to look at 2.43. I just saw the latest code stream available. I downloaded it, compiled it.
Any idea that it would be the same as 2.43?
I had some benchmarks at customer sites running 2.42. I didn't run IOR to baseline those tests because they were running commercial-specific codes. It's hard to say without data if there was any improvements with 2.43, but it's worth something I could really compile and just run a synthetic benchmark.
Okay, thank you.
Okay. Thanks, Andres. So according to that, they should be performing the same.
Hey, John. I just wanted to point out that the reason why your benchmark results didn't change with 1.8 is because you were doing direct I/O, and direct I/O doesn't even take those tunables into account. I think you would see dramatic differences in buffered I/O tests. And then I just wanted to ask you a question about, I think you answered it. You said you ran these scripts, you did the writes and then the reads back. So you read back each new set of files from each set of scripts, right? You didn't have one set of files.
No, that's right.
Okay.
So every time I wrote, it was a new file name and a new set of test data created. And then that read for that test case would read back that same test file. The next test would write a new set of files and read back that same set. It was never reading back the original file. Every test that we did, when we increased the number of threads or increased the max RPCs in flight or changed checksums, always paired the two reads and writes together, but those pairs are very different in the file names.
Yeah, thanks. I didn't see this in your data, but we've seen read back results change when you write down the data on the platters differently. So,
okay. Yeah. And I saw that slightly too as well, because the more that you write the data. What I did was after I read it, I had IOR delete those files. I didn't keep it on the file system.
I was curious if you looked at why the performance dropped at the end as you increased thread counts on the client.
I looked at that result, so timing is everything. I wanted to have more time looking at that, but I ran out of time, so I just decided to share the results, point out the interesting data point, but that is something I want to look back and see why it tapered off like it did and where 189 did not. Thank you.